Good morning. I'm going to wait until all our viewers are here, and I'm just trying to get Bug to eat his breakfast. Good boy. He's a really picky eater. And I have to sit by him calmly in order to get him to eat usually. Good boy. Once he gets started, I can leave him. That was good. Good job, Bugs. Good job. Good morning. I only see 9 concurrent viewers. I'm going to wait about 1 or 2 more minutes and then I'll get started. Good boy. Start in about 1 minute here. All right. Once he starts, it's kind of like a snowball effect. Once he starts eating, he doesn't need me anymore. He just needs me to get started. All right, class. Good morning. Happy Monday. Today is going to be our last lesson on kinematics. And then we're going to move on to our next topic. So let's go ahead and get started. So today's lesson is on something called projectile motion. So projectile motion refers to any motion that is due to gravity. Okay, so I'm going to call it maybe two-dimensional motion under the influence of gravity. Okay, so sort of the picture you want to have in your head of projectile motion is maybe there's a cliff, okay, and something gets thrown off the edge of the cliff and it flies through the air and it hits the ground, okay? So that's two-dimensional motion. The thing is moving horizontally and vertically, okay? All right, and so we want to be able to predict things like, well, how much time is it going to take to hit the ground? How far is it going to go? Things of that nature, okay? So projectile motion is sort of inherently two-dimensional, right? So one of the things we're going to be dealing with is velocities that are not horizontal or vertical, but diagonal. So what I want to talk about briefly is how do we deal with velocities that are diagonal, okay? Dealing with diagonal velocities, okay? So as an example, let's suppose that we have a velocity where maybe this is a velocity that is, I don't know, 50 meters per second in that diagonal direction, okay? So what we want to do is we want to think about this velocity as a right triangle, okay? So I sort of make a right triangle out of the velocity, like so. And I would specify whatever this angle is. So this is called the angle with respect to the horizontal. And so let's say that angle is 30 degrees, for example. All right. So if you want to know, if you have a diagonal velocity, that diagonal velocity can be thought of as a horizontal motion combined with a vertical motion, okay? So we're actually going to use trigonometry to get how much of this velocity is vertical and how much of this velocity is horizontal, okay? So if we want to know how much is vertical, we're going to be using the sine function. Now, why is that? Because if we look at this leg of the triangle, see how it is opposite the angle? And if you remember, your sine is opposite over hypotenuse. See how sine has opposite in it, and this side is opposite the angle, okay? So, anyways, so this is going to be 50 sine of 30 degrees, which would be 25 meters per second. All right? And then if we think about this leg of the triangle, this horizontal leg, it is adjacent to the angle, and cosine is adjacent over hypotenuse. So we're going to be using the cosine function to get this leg of the triangle. So it's going to be 50 times cosine of 30 degrees. And need a calculator for this one. This is going to be 43.3 meters per second. All right. So what that means is that a 50 meters per second velocity at an angle of 30 degrees to the horizontal is equivalent to motion that is 25 meters per second up and 43 meters per second to the right. Okay, if you combine those two motions, you get 50 meters per second at an angle of 30 degrees. Okay, one thing you want to keep in mind is that these two velocities add up to more than 50 meters per second, but you have to keep in mind that in order to get the speed is basically the hypotenuse of the triangle. Okay. So in order to go from these two to get the speed, we have to do the Pythagorean theorem. We don't add together the two velocities, we do the Pythagorean theorem. Okay? Let's talk about a couple of special cases. What if the angle of launch is 0 degrees? Okay? That's called a horizontal launch. Okay. So if the angle of launch is 0 degrees, it looks like this. Okay. So that has, so maybe 50 meters per second like that. And if we think about that, that has a vertical part of that velocity is 0, and the horizontal part is 50. Okay, so this is a velocity that is entirely horizontal and none of it is vertical. Okay, if you have a vertical launch, then that means that the velocity is 100% vertical and 0 horizontal. Okay, so go ahead and type it into the live chat if you know what is the angle of launch for horizontal and what is the angle of launch for vertical. This being the angle of launch. Okay, and while I wait for your responses, these have a name. These two velocities have a name. This is called the vertical component of the velocity, and this is called the horizontal component. Okay. Excellent. Yeah. So the for a horizontal launch, you could think about the angle as 0, and for a vertical launch, you could think about the angle as 90 degrees. Okay. Very good. So now we're going to talk about the equations of projectile motion. So there are two equations. Okay, and they're both based on the first kinematics equation. So remember, the first kinematics equation was delta x equals v naught t plus 1/2 a t squared. All right, because projectile motion is two-dimensional, you are going to have two equations. You're going to have an equation for delta y, and you're going to have an equation for delta x. So your delta y equation is going to be vy naught times t minus 1/2 gt squared. Okay. So notice how this has the same structure as our delta x equation. Okay, it has a constant velocity term and it has an acceleration term. The delta x equation is simply vx naught times t. Okay. So let's have some discussion about this. First of all, you will notice that there's v naught became vx naught and vy naught. Now, why is that? Because when you launch a projectile, you can launch it at an angle. Okay, so here's your initial velocity after the launch. Okay, so v naught is the launch speed, and you have a certain launch angle. Okay, and the launch speed and the launch angle determine the initial y component of the velocity and the initial x component of the velocity. So if you know the launch speed and the launch angle, you use trigonometry in exactly this manner to determine how much of that is vertical and how much of that is horizontal, and you would use those in these two equations right here and here. Okay? So that's my first comment. That's how you determine vy naught and vx naught. My second comment is we notice that this has a t squared term. The t squared term is where the bendiness comes from. That's where the acceleration comes from. Okay, The delta x equation has no t squared term. Why is that? That's because gravity makes something accelerate vertically, but gravity doesn't pull horizontally, okay? So there's no horizontal acceleration, all right? However, there is a vertical acceleration. So I'll put a little comment here. There is no horizontal acceleration. Okay? There's no t squared term in the delta x equation. However, there is in the delta y equation. And furthermore, we notice that there is a minus sign here. And the minus sign indicates that gravity causes things. Gravity accelerates things downwards. Okay? And then, of course, I have g, which stands for the acceleration due to gravity. Which, if we were on Earth, this would be 9.8 meters per second squared, which we round to 10 meters per second squared. Okay? Keep in mind that the variable g is defined as having a positive sign. So, so the acceleration is, so there's no double negative here. There's only one negative, and it's coming from that spot right there. Okay? If you put in a double negative, then that would represent anti-gravity, causing things to accelerate up into the sky. Okay? So these are the two equations. These are the important equations for today. So the rest of this lesson is just devoted to some examples, okay? And there are 3 examples that I would deem to be important, okay? Oh, by the way, one of the things I wanted to say is that the initial velocity vector might look like one thing, but the velocity is changing because of the acceleration due to gravity, okay? So if you look at a projectile, while it's being launched, its velocity, the angle of the velocity is changing, and the speed is changing. So while this might be the direction of the initial velocity, gravity is going to curve that velocity into a different direction, okay? So these variables are referring to the velocity components at launch, not after launch, okay? So the first example that I want to do is horizontal launch off a cliff. Horizontal launch off a cliff. So, why is Claremont Unified calling me? Hang on one second. Hello? Okay. Automated message. Did anyone else just get an automated message from Claremont Unified School District? Okay. So, I thought maybe because the other day I was teaching and I got a message from Doc Ock, and it was talking about how he was asking me like, oh, are you teaching right now? Because he didn't realize that I was doing my lessons on YouTube. And so he went to my Zoom room, and my Zoom room wasn't open. So he's like, what is this guy trying to pull? And I was like, dude, I'm on YouTube. Okay. So here's the scenario. You were dumped by your significant other. Okay? You go to the edge. Now this is going to sound dark before I explain the problem completely, but it's not dark. You go to the edge of a 120 meter tall cliff. And throw. Now, when you first started dating this person, they made you a mixtape of all the songs that that reminded. They made a mixtape for you. Okay, and so now you got dumped, and you still have this mixtape, and you're like, what do I do with it? So you throw the mixtape off the cliff horizontally at 50 meters per second. Where does it land? By the way, this is not realistic at all, because if you could throw a mixtape at 50 meters per second, you should be playing baseball, because that's like over 100 miles per hour. Okay, so keyword here is horizontally. All right, so let me just draw the scenario. Here's the cliff. The cliff is 120 meters high. Here's you. And we're going to assume that your height is negligible compared to the 120 meters. Otherwise, we would technically have to add to that the height of your hand when you released it, right? So you throw the mixtape. Here's the mixtape. You throw it at 50 meters per second. It goes and lands right there. We want to know, what is this distance? So basically what we're trying to find is delta x. All right. So the first thing I'm going to do is I'm going to set up my two projectile motion equations. So I have a delta x equation. And the delta x says Vx initial. What is the initial x component of the velocity? Now, because this was a horizontal launch, all of that 50 meter per second velocity was horizontal, and none of it was vertical. Okay? Of course, after you release the mixtape, it's going to acquire a vertical velocity because of gravity, but it starts out with all of that velocity being vertical, or horizontal, excuse me. So that's delta x equals 50 times time. Okay? For our delta y equation, because it was a horizontal launch, none of the initial velocity was vertical. Okay? So this term just goes away. It just goes away. I'm not going to actually cross it out, but it goes away, and all we have is this term. All right? So we have this. Now, 1/2 g is going to be 10 divided by 2, which is 5. So we have minus 5t squared is our delta y. All right? So these are our two equations of projectile motion. Now, the strategy, generally speaking, in projectile motion problems is what you do is you figure out the time of flight. How much time is this projectile in the air for? And then you figure out, once you know the time of flight, you figure out how far does it go. Okay? So I have to figure out the time of flight. Now, the thing that determines when this hits the ground is the mixtape has fallen 120 meters. Okay? So that means that delta y is negative 120 meters because it fell 120 meters to go from the cliff all the way down to the ground. Okay? So I have negative 120 equals negative 5t squared. So I plugged negative 120 in for delta y. And so dividing both sides by negative 5 gives me, 24 equals t squared. So that's going to be a little less than 5. 4.9 seconds. So it is going to take 4.9 seconds to go for the mixtape to go from here to the ground. Okay. Then, once we've solved for the time, we then can plug that into our delta x equation and solve for delta x. So we have delta x equals 50 times 4.9 is 245 meters. So that's how far horizontally this mixtape is going to go before it hits the ground. Okay? So that's a great example of projectile motion. We're going to do 2 more examples here. Okay. Using a different pen and it kind of bleeds through a little bit, doesn't it? So for our next example, I'm going to call this angled launch across a level surface. Okay, so a good example of this is something like a military sniper. Ooh, this is going to be a scary problem. Okay, so we've got a military sniper. Here's the ground. Here's the ground. Okay. And let me make a. So there's the sniper rifle. That. So there's the sniper, okay? And they launch a sniper rifle bullet at 500 meters per second, okay? Now, I'll say something in the Zoom call about this, but you might actually not, this is faster than the speed of sound. You might actually not want your sniper rifle bullet to go faster than the speed of sound. That could be bad. So, but I'll talk about that in the Zoom call. And you launch it at an angle of 10, let's say 7 degrees above the horizontal, okay? So the sniper rifle bullet goes, okay? And we want to know, how far does it go? All right? So, because this is an angled launch, it becomes important to do the trigonometry. Okay, we have to create a velocity triangle to get the components of the velocity. Okay, so that's the first thing you want to do if you have an angled launch, is you want to get the components of that initial velocity. So we have 500 meters per second launched at an angle of 7 degrees. So that means our initial vertical velocity is going to be 500 times sine of 7 degrees. You want to make sure that, because we're using trig functions, you want to make sure that we're in degree mode. A great way to check if you're in degree mode is to just do sine of 90 degrees, which is 1. So see how I got sine of 90 degrees is 1, so I feel confident that I'm in degree mode. Okay, so I go 500 times the sine of 7, and that gives 60.93, which I'm going to round to just 61 meters per second. Now you are doing, you have that 2% margin of error, so maybe you would write down 60.93 or something like that. To get the horizontal component of the velocity, we have 500 times cosine of 7 degrees. All right? So I delete 500 times cosine of 7 is 496 meters per second. All right. So now I go to, so this is Vy naught, and this is Vx naught. Okay. Give me 1 second. I forgot to change. Need to change a setting on this stream. Okay. So so now we will go to our delta x equation, which is Vx naught times time. So that's going to be 496 times time. Our delta y equation is going to be Vy naught times time, so 61t minus 1/2 gt squared, so minus 5t squared, like that. Okay? So, what does it mean when the projectile hits the ground? So, we're always going to have in the projectile motion problems, you have to come up with some mathematical statement of what does it mean when the problem is done, okay? And if we think about this problem, it starts out, the projectile starts out at ground level, it goes up in the air, and it comes back, and it returns to ground level when it hits the ground. So the starting elevation is the same as the ending elevation. So it's just like the chicken wing problem that comes up and it goes back down. Okay? So our condition where the problem is done when delta y equals 0. Okay? That's our condition for the projectile is done flying. Okay? So I'm going to plug that into the delta y equation. We have to solve the equation 0 equals 61t minus 5t squared. Okay? Add 5t squared to the other side. 5t squared equals 61t. I'm going to divide both sides by 5. So that's going to give me 12.2. T squared equals 12.2t. And then now lastly, we're going to divide both sides by t. Now, whenever you divide by a variable, you have to be careful that that variable is not equal to 0. And I know that time is not equal to 0 because I know that it's not an infinitely fast projectile, okay? So I know it's going to take at least some small non-zero amount of time to go from point A to point B. So I can divide both sides by t, and I get that t equals 12.2 seconds. Okay? So there you have it. So that's the time of flight. But now I want to know how far is it going to go in that amount of time. All right. So to do that, I would use my delta x equation. So delta x is going to be 496 times the time, which is 12.2. So I have 496 times 12.2 equals 6,054. So I'm just going to say roughly 6,000 meters, which is 6 kilometers. Okay. So that's an example of an angled launch across a level surface. This answer is almost surely going to be much less accurate than this answer. Okay? Why do I say that? Because the faster a projectile goes, the more it is influenced by air resistance. Okay? So if you have an angled launch across a level surface, it is going to be much more affected by air resistance because it's going at 500 meters per second versus 50. Okay? So this is kind of just a ballpark estimate. This would be really accurate if you were projectile launching on the moon where there's no air resistance, but in the case of just on Earth, this is not going to be terribly accurate. So just keep that in mind. It's just an estimate. All right. So we'll do one more example, and then we'll switch over to Zoom. For this last example, you are egging a friend's house. Actually, why would you egg a friend's house? Maybe you're egging an enemy's house. Okay. You throw an egg. At 45 degrees above the horizontal. With speed, let's say 25 meters per second. You are standing 15 meters in front of the house. Where does the egg land? Okay. So let's draw this scenario, and we're gonna neglect your height, and we're gonna assume that you're, you have a height of 0 meters. So let's see. Here's the house. I'll draw your standard picture of a house as if you were a kindergartner. There's the house, okay? And here you are egging a friend's house, okay? Launch that projectile, and it's going to go splat right here, okay? And what I want to know is, where does it land? How high up does it land? What is delta y? So this problem is different because in the previous problem we were trying to figure out what is delta x. Now we're figuring out what is delta y. The egg has to travel 15 meters horizontally, and it is launched at 25 meters per second at an angle of 45 degrees. Okay, so I'm going to just really quickly get the equations of projectile motion. So this is 25 meters per second at an angle of 45 degrees. Now, one of the things about 45 degrees is it's diagonal. It's like 100% diagonal. So you actually have an even split between vertical and horizontal. Sine of 45 is equal to cosine of 45. So this is 18 meters per second, and this is 18 meters per second. Again, 45-degree launch is an even split between vertical and horizontal. All right. So, so what we're going to do then is plug this into the equations of projectile motion. So delta x equals 18t. Delta y equals 18t minus 5t squared. So what does it mean to hit the house? What is the mathematical condition that means you hit the house? Well, you hit the house when the egg has traveled 15 meters horizontally. Okay? So 15 meters is delta x for this problem. So to get the time of flight, what we would do is we would take our delta x equation and we would say 15 equals 18t. So this is our delta x equation with a specific value for delta x plugged in. Divide both sides by 18. And we get, it's going to take 0.83 seconds to impact the house, which we then plug into our delta y equation, and we can figure out how high up on the house it's going to hit. Okay? So delta y is going to be 18 times 0.83 minus 5 times 0.83 squared. Okay, I'll crunch the numbers on that quickly. And we get that it is going to land 11.5 meters up on the house. Okay, so let's suppose that the house is less than 11.5 meters tall. Then that means that the egg went over the top of the house. Okay, maybe it lands on the roof on the way back down, but we don't know. So if the house is less than that, so this is it would have to be a pretty tall house for this to work. That's all I'm going to say. All right, so that is my lesson for today, so I will meet you in the Zoom room.